Hello dear students, this is class 11th lecture and related to physics very important chapter, that is what? Thermodynamics. And in thermodynamics the basic terms, that is in thermodynamics is what? Heat, and dynamics is what? That is movement. Here this thermodynamics consists of two terms, that is temperature related terms heat and motion related term, that is movement. Clear? So starting from heat is a form of energy that gives the sensation of anybody either hot or cool. Clear? If anybody having greater temperature, then body is hot. If anybody having lower temperature, that is totally based on what? Totally based on temperature. If temperature a body is greater, then body is said to be hotter body, and if temperature is lower, then body is said to be colder body. Clear? And movement means just like anybody move from one point to another point. Or here we will discuss about the gaseous molecules, how the gaseous molecules move from one point to another point. Basically in system, I will say that in cylinder how gaseous molecules move, and whenever gaseous molecules move, then we will discuss about pressure, volume and temperature. Basically all these three terms we will discuss in this chapter, and along with these three terms we will discuss what? Also internal energy, and that internal energy is what? Combination of potential energy and kinetic energy. This one UK for kinetic and UP for potential energy, and some more terms related to that particular chapters, that is density, and you say that some concept of work done also available in this chapter. So starting from thermal equilibrium, the basic term is what? Thermal equilibrium. How you just say that body is in thermal equilibrium without knowing about temperature? You can't justify the body is in thermal equilibrium or not. Suppose two body A and B separated by a specific wall, diathermic wall. Then and initially the body A's temperature is T1 and body B temperature is T2, and here what? T1 is greater than T2. Then initially when T1 is greater than T2, then when they connect with a diathermic wall, body A and body B, these two bodies connected through this diathermic wall, then after some time their temperature becomes what? After some time their temperature becomes T, and that is what? Approximately equal to T1 plus T2 upon 2. That is a common temperature of both the body, and this common temperature gives what? An indication about the thermal equilibrium of these two body. And this thermal equilibrium achieved only on behalf of this diathermic wall. Diathermic wall means a wall, I say that a medium through which Heat can transfer from hotter body to colder body. Clear? This is the transfer of heat, and heat representing by Q, and always flows from higher temperature to lower temperature. Clear? And suppose if you just separate these two body with the help of adiabatic valve. Suppose here two body A and B are P and Q, no matter, anyone you can assume. Two body P and Q separated by diathermic, not adiabatic valve. Adiabatic valve, and here what? Having temperature T1 and this one having temperature T2. Here T1 is less than T2. Then we can't justify after some time the body will achieve the thermal equilibrium. Why? They did not achieve the thermal equilibrium because the basic concept is what? There is no chance of transferring heat from P to Q or Q to P. Further, from P to Q impossible because the temperature of body Q is what? Greater than body P. So if a chance of transferring heat, then from Q to P will occur. But due to this adiabatic valve means a valve or a medium which do not allow heat from one body to another body through them. Clear? This valve do not allow heat transferring from Q to P or P to Q. Either temperature of Q is greater or P is greater. Whenever here temperature of Q body is greater than P, then heat transfer will be from Q to P if possibility is here, but there is no chance of transferring from heat Q to P. So this case of combination of two bodies is not in thermal equilibrium, but in this case the two bodies A and B are in thermal equilibrium. How they achieve thermal equilibrium? Because there is a possibility of transferring heat from body A to body B. Why from body A to body B? Because body A having temperature greater as comparison to B, then temperature greater means what? Heat having greater temperature flowing from lower temperature, flowing from greater temperature to lower temperature. Clear? So this is the concept of thermal equilibrium. Thermal equilibrium is a concept in which two bodies attain a common temperature, when they connected through a diathermic valve and initially having different temperature. Clear? So after this, the next important thing is what? That is zeroth law of thermodynamics. Zeroth law of thermodynamics, very important topic. Yes. Note down all these terms. Very easy. What is the concept of thermal equilibrium? Thermal equilibrium concept means what? When two bodies attain common temperature, I will say that equal temperature or average temperature or same temperature, no matter, you can use any one word for this thermal equilibrium. And the concept of diathermic and adiabatic valve, very important for explaining what? Zeroth law of thermodynamics. Let's see, zeroth law of thermodynamics. Zeroth law of thermodynamics, very easy concept. Only when the diagram concept, whenever clear, then you can explain about these law, this concept. Zeroth law of thermodynamics gives the concept of temperature also. Concept of temperature. You see, two condition of three different body. Some one condition body A connected with two body B and body C. The condition was B and C. These two bodies are separated from each other by a adiabatic wall, but B and C are connected through A with the help of diathermic wall. With the help of diathermic wall. Just see what will happen. Very simple concept of zeroth law of thermodynamics. When you understand about the diagram, then you can write down within 2 to 3 lines about this law. This is body A, and this one is body B, and this one is body C. Only on the replacement of what? Diathermic and adiabatic. Here this one is diathermic, and this one is adiabatic. Adiabatic wall. This one adiabatic wall, and this one diathermic wall. Let's see. Here three bodies we are taking: body A, body B, and body C, and two types of wall. First, diathermic wall, and second, adiabatic wall. Diathermic wall means a wall which allow for transferring of heat from one body to another body if there is a difference of temperature. Just see in this set of diagram, this is figure first, this one is figure second. Okay, just see from starting. Here two bodies B and C are separated with each other through a adiabatic wall. It means there is no chance of heat transferring from B to C or C to B through this wall. Clear? But with the help of this wall, diathermic wall, heat transfer from B to A and also from A to B, and same as for C through this diathermic wall. It means heat transferring is allowed from either B to A or A to B, and further from C to A or A to C. It means just after some time, when body A, B and C are arranged in this way, then temperature of body A that equals to temperature of body B temperature equal to A. Okay, just see temperature of body B equal to what? Temperature of body A, and temperature of body C is equal to temperature of body A. It means what? Here right side A, then left side must be equal. This implies that T B is equal to what? T C. It means body B temperature becomes equal to what? Body C temperature. Why? With the help of this diathermic wall. And how these particular conditions obtained are just confirm. Both B and C are in thermal equilibrium. Just after some times, when the diathermic wall and adiabatic wall just replaced, then it is obtained that what? There is no transferring of heat from either B to C or from C to B. But here the chance is available for transferring of heat from B to C or C to B. But already B and C are in thermal equilibrium with this configuration. Here, that's why in this configuration there is no transferring of heat from B to C or from C to B. It means body B and body C are in thermal equilibrium with each other along with body A, as like in previous case. Just like case number first, figure not first indicates that what body B and body C comes in thermal equilibrium with a third body A with the help of this diathermic wall. Clear? And this B and C, after replacing their walls, there is no transferring of it from B to C and C to B. It means both body B and C attains what? Equal temperature. And the statement of this law, zeroth law, you can write down: when two bodies are in thermal equilibrium, two bodies means what? Here for body B and body C are in thermal equilibrium with a third body C, then body B and C, starting two bodies, must be in thermal equilibrium with each other. Clear? Statement very simple. When two bodies are in thermal equilibrium with a third body, then the two bodies must be in thermal equilibrium with each other. Clear? So the whole diagram and the explanation of this zeroth law very important, very easy. And with the help of this zeroth law of thermodynamics, we can explain what? The concept of temperature. Concept of temperature means a physical quantity. A physical quantity. This concept of temperature only for physical quantity. That determines the two bodies are in thermal equilibrium or not. If initially the temperature is same for both, and finally after some time the temperature is same for both, then means what? Both the body are in thermal equilibrium with each other, and that particular quantity which determines the thermal equilibrium state, that is what? Temperature. Clear? So all about the zeroth law and concept of temperature. Further, if you have any query, then you can ask. But just after zeroth law of thermodynamics, the concept of temperature, the next thing is what? Very easy and very important. That is what? About first law of thermodynamics. Let's see. First law of thermodynamics. First law of thermodynamics. First law of thermodynamics related to your own daily routine concept. How you can correlate this law with your daily concept. That is what? We are all doing work on behalf of gaining energy, and that particular work having some utilization of the energy, and the remaining part of the energy that is in the form of development of the body. That is what? Suppose dq amount of heat is given, a dq amount of energy is taken, then this amount of energy is utilized in two ways: in increasing the internal energy, that is development of the body, and also in doing some work. This is the mathematical form of first law of thermodynamics. Very easy. In simple way, you can write what? Energy can neither be created nor be destroyed. The total amount of heat energy, that is in the form of two way. First form, in doing some additional work or work against the pressure, and some part of heat energy that is in the changing internal energy. Clear? So on behalf of this first law of thermodynamics, we will explain about all the thermodynamical process. The thermodynamical process, just see how many thermodynamical process. Thermodynamical process. First, isothermal process. Isothermal process. Isothermal, very easy. That is, temperature remains constant all over. Whenever temperature remains constant, iso means what? That it for same value, and thermal means temperature related. A process in which temperature remains same all over the process, that is an isothermal process. It means what? T1 is equal to T2, or you say that dt is equal to 0, dt is equal to 0, and the very basic concept is whenever the change in temperature is 0, then internal energy change of an ideal gas, always remember, for an ideal gas, internal energy totally depends upon what? Temperature concept. Totally depends upon temperature. Internal energy of an ideal gas totally depends upon temperature. Whenever there is no change in temperature, then there will be what? No change in internal energy. Clear? It means du must be 0. And in case of isothermal process, then dq is equal to what? dw. Clear? For isothermal process, always remember dq is equal to dw. Clear? And then after your isothermal process, the next one is what? Adiabatic process. Adiabatic process. In adiabatic process, nothing just different. Only one, there is no chance of transfer of heat from one body to another body or from another body to one body. Clear? Only one, the concept of change in heat, that is dq. It means what? The body or the system neither taking heat from surrounding nor transferring heat to the surrounding. It means change in heat energy. I will say that dq is equal to what? 0. dq must be 0. Second case, let's see adiabatic process. Adiabatic process, dq is equal to 0. In this case, from first law of thermodynamics, 0 is equal to du plus dw, or du is equal to minus dw. Clear? If work is done on behalf of the gas, then internal energy or decreases. Internal energy decreases. dw is equal to minus du. Here, the next one is what? After this adiabatic, isoporic process. In isoporic process, isoporic means same volume. There is no change in volume. It means what? V1 is equal to V2. V1 is equal to V2. I will say that dV is equal to 0. But always remember, work done, the small amount of work done, that is force into displacement. But force means what? Pressure into area. Pressure into area. And area into displacement is what? That is volume. P dV. So work done in the form of pressure, that is pressure into volume. Always remember this one formula for work done. P dV. Here dV is 0. Then dW must be 0. dW must be 0. So by first law of thermodynamics, dq is equal to du plus 0. A total dq is equal to du. Clear? This is the isobaric process concept, and the next one is what? Isobaric. In isobaric process, there is always a concept of work done. So first law of thermodynamics, very simple way. dq is equal to du plus dw, that is equal to what? Du plus p dv. This is the formula for dq. Here no term becomes 0. But in case of free expansion, in case of free expansion, always remember dq will be 0, dw will also be 0, and then when dq 0, dw 0, then du must be 0. In case of free expansion, that is the very special case. So just after these cases, we will start discussion about the two terms in detail: isothermal process and adiabatic process. And always remember, there is two equation of state, one for isothermal and second for adiabatic. In the whole chapter, we will follow two equations of state. Let's see. First, isothermal equation of state. That is PV is equal to what? Constant. And adiabatic equation of state. A simple specific molar specific heat ratio will include, that is PV power gamma equal to constant, where gamma equal to Cp upon Cv. Here this Cp, that is molar specific heat at constant pressure, and Cv means molar specific heat at constant volume. Just note down all. We will discuss about these two equations in details. I will say that the concept of isothermal and adiabatic in the terms of pressure, volume and temperature, you can find out the relation among any two or three with the help of gas equations. Clear? So just note down. Suppose the concept of equation of state for adiabatic in terms of pressure and temperature, then how you correlate? Let's see, pressure and temperature concept. P V power gamma is equal to constant. Constant means nothing, just constant K. But PV is equal to RT for 1 mole of gas, Let's see. After this, PV is equal to RT. The value of V is equal to what? RT upon P. Then put this value in above equation. Then P RT upon P power gamma is equal to constant. Then this pressure is alone, but this pressure is what? Power gamma. Then will be what? P power 1 and R power gamma, T power gamma upon P power gamma is equal to constant. Then after this, the next step will be P power 1 minus gamma, T power gamma is equal to what? Constant. This R power gamma transfer towards right side, then constant upon constant will give what? Another constant, and here this gamma p power transfer in numerator side will be what? Minus gamma, will be minus gamma, then 1 minus gamma. This is the relation between pressure and temperature. Similarly, you can find out the relation between volume and temperature. Volume and temperature by replacing this P is equal to what? RT by V. RT by V. So in this way you can find out, no matter, very easy concept. Just after this, you will derive the work done formula. Work done formula, very important formula. Work done. Work done in isothermal process and work done in adiabatic process. Just note down this one, very easy. Then after this, work done in isothermal and adiabatic, in both cases, the concept of this small amount of work done will utilize directly, and that particular two equations of state also used directly. Work done is what? That is the concept of force and displacement in case of first isothermal process. Work done for isothermal process. Work done in isothermal process, no matter, isothermal process. See, small amount of work done, PW is equal to PdV, that from force into displacement, and this force equal to what? Pressure into area, because pressure is equal to, you are knowing very well, pressure is equal to force upon area, then force equal to pressure into area, then area into displacement, area into this displacement. How gives volume? That is very simple. A cylinder having area A, and if this displacement is what? Distance is what? dx, then area into height, just like pi r square h. This pi r square is A and h is dx. A into dx, this pi r square is volume, this A into dx what? Also representing volume. Clear? So in this way, the concept of work in the terms of volume, very simple. After this, the total amount of work done, only one integrating from V1 to V2, this amount of work done, that is PdV V1 to V2. Just see, here PV is equal to constant, PV is equal to constant, take this one constant K, then you have to replace what? P is equal to K upon V, K upon V. Let's see, integration V1 to V2, K upon V, dV is equal to what? K constant taken outside, integration 1 upon V, always remember 1 upon V, that is log to the base E, V, V1 to V2, then this gives what? K log, this K must be replacing by RT, no matter, we will use RT directly. This K to the base E, first upper limit minus lower limit, that is equal to V2 upon V1. Replacing K by RT, K by RT, then W equal to RT, and that particular log E in the terms of common log, then 2.303 3 log to the base 10 V2 upon V1. V2 upon V1. Clear? This is the work done formula. Just note down this one, very important, very easy formula. The concept of either work done in isothermal process or adiabatic process, you can derive anyone, no matter, very easy. Same as isothermal, you can derive adiabatic process, work done in adiabatic process. The concept will be same, but something will be different. That is what? The formula. Let's see how to derive the work done in adiabatic process. Adiabatic process having a specific equation P power gamma equal to a constant. Small amount of work done, PW equal to PdV in adiabatic process. In adiabatic process. How to calculate the work done in adiabatic process? We are knowing what? PV power gamma is equal to constant K, or you say that RT. K or RT. No matter, you can use anyone. Then total work done. But you have to integrate this one from V1 to V2. So replace this power, not power, pressure in the terms of volume. It is equal to what? You are knowing this pressure in the terms of K upon V power gamma dV. Okay, this is the amount of work done for very small value. So total work done, let's see, dW equal to what? V1 to V2. dW, this is the total work done, and integration from V1 to V2, value of dW, K upon V power gamma dV, and K constant term, so taken out, integration V1 to V2, 1 upon V power gamma dV. Then this 1 upon V power gamma when transfer from denominator to numerator will be what? Minus gamma. Then this W equal to what? Integration this K V1 to V2 V power minus gamma dV, and this minus gamma just operate on this particular formula, integration of x power n dx. It gives what? X power n plus 1 upon n plus 1. And then after integration we will use what? Upper limit and lower limit. It gives K V power minus gamma plus 1 upon minus gamma plus 1 V1 to V2. Then W equal to K upon 1 minus gamma. This V first replacing by V2 power 1 minus gamma and V1 power 1 minus gamma. And equation of continuity in the terms of equation of state. Just see how this one you apply. P1 V1 power gamma is equal to what? P2 V2 power gamma, that must be equal to K. Any one value you can use at the place of K, either P1 V1 or P2 V2. So multiply first K 1 upon this 1 minus gamma. It gives what? K V2 power 1 minus gamma minus K V1 power 1 minus gamma. Just see this K one time using at this V2 resolving V2 here, so K value P2 V2 power gamma will be P2 V2 power gamma. So W equal to what? 1 upon 1 minus gamma will be same P2, and when V2 power gamma, then 1 minus gamma. Let's see, V2 power gamma and 1 minus gamma. When you use, let's see here, will be what? V2 power gamma and V2 power 1 minus gamma, then V2 power 1 minus gamma plus gamma. Gamma gamma cancel, that gives what? V2 only. So we will use what? P2 V2 minus mx P1 V1, and we are knowing what? P1 V1 whenever taken, then R T1 and P2 V2 whenever taken, then R T2, then R common, so R upon 1 minus gamma, then T2 minus T1. This is the equation for work done. Clear? So up to work done, you will revise up to 2 to 3 times, then everything will be clear. And in next lecture, we will discuss about the concept of second law of thermodynamics and Carnot cycle, that is also very important, and heat engine and refrigerator. And within 2 lectures, this chapter will completely finish, and after these 2 lectures, we will solve some numerical based on each topic. Clear? So you will revise up to work done by isothermal process or work done by adiabatic process. In adiabatic, R upon 1 minus gamma T2 minus T1. In isothermal, RT 2.303 log to the base 10 V2 upon V1. Clear? So that's all for today. Have a nice day.